Okay, thanks everyone. So I'm Ankit DISA. I'm actually one of the organizers of this workshop. So first of all, I want to say thank you everyone for coming. Second, as one of the organizers, you often have to fill in when things go wrong. So Rick Averitt was supposed to give this talk, but I will do my best to do a Rick Averitt impersonation here. And so I kind of took that as a little bit of a cue. And so I made the title of my talk, Light-Driven Control on Dynamics and Correlated Magnets, which was as close as possible as I could get to Rick's title of Dynamics and Correlated Antiferromagnets. So I'm actually going to be talking about ferromagnets, so that's why I couldn't quite put it in there, but it's pretty close, like 80% overlap, so hopefully it'll be okay. So what I'll tell you about is actually work that I did before I went to Cornell. Our lab is still getting up and running. If I have time at the end, I'll give you a peek of some of the stuff that we're doing there. But I'll tell you about work that I actually did while I was in Hamburg in the group of Andrea Cavalieri, using tailored terahertz light pulses to control, in particular, magnetic phases of correlated materials. Okay, so we already heard a lot about correlated materials. And from my standpoint, the very useful thing is that in these types of systems, generically, the behavior of the crystal lattice is strongly intertwined with the orbital, spin, and charge degrees of freedom of the electronic sector, right? And what Andy just showed us is this can lead to very complicated free energy landscapes where you have a number of different nearly degenerate ground states that arise because of the competition and cooperation between these different degrees of freedom. And a consequence of that is what kind of Harold showed us, was that you end up with very, very complex phase diagrams where you can tune the ground state of the system between different types of phases by applying some external perturbation, as we know, for example, pressure, doping, strain, et cetera, et cetera. But where I come in is the observation that even in this case, we have very, very unusual and interesting phases. We're still in some sense limited because often the temperature of these interesting phases is maybe too low, or they appear at too high of pressures. And so what we would love to be able to do is to actually go beyond somehow this phase diagram so that we can induce new phases and functionalities. And of course, as many of us do, the way we do that is by applying ultra-short light pulses that allow us to dynamically drive the system out of equilibrium and access new phases and functionalities that don't otherwise exist that can happen on ultra-fast timescales and, in many cases, give rise to properties that are beyond what are possible in the equilibrium setting. And one of the reasons, you could drive your system in many, many different ways. Why do we use light? I think many of the people in this audience know this. But the reason that I find light very useful is that you can use the frequency degree of freedom, the energy degree of freedom of your photons to couple selectively to the various degrees of freedom of your matter system, right? So by tuning the frequency of your light pulse, you can couple to the magnetic order, the charge order, or for example, the lattice order. And this is something that I've been particularly interested in doing and that they do a lot in Hamburg, which is motivated a lot by the observations that the crystal structure that is very, very intimately tied to the electronic properties of the system, as Harold showed very exquisitely in this thin film geometry. So we can take advantage of that and not only, let's say, use light in a spectroscopic sense to probe the structure, but we can also use it to drive the structure into new, drive the lattice into new structures if we use sufficiently strong laser pulses. So we spend a lot of time in Hamburg, and I spent a lot of time during my postdoc developing laser sources that allow us to actually resonantly drive the lattice vibrations, the phonons of the system, to very, very high amplitudes. It's a somewhat non-trivial task, but I can tell you that now we have lab-based sources that allow us to really access nearly the full range of phonon frequencies in most complex crystals with electric field strengths on the order of megavolts per centimeter. And this can lead to essentially atomic displacements on the order of 5 or 10% of the equilibrium bond length, right? And so with these huge atomic displacements, the response of the crystal lattice is highly nonlinear, and that allows you to access new crystal structures that don't exist in equilibrium, which then come along with new electronic and magnetic properties. This is the generic idea. And what I wanted to do first is show you a quick example of an experiment that we carried out a couple of years ago that demonstrates how this works. So what we did was we looked at this very simple antiferromagnetic system, cobalt fluoride. What you need to know basically is that it has two sublattices of cobalt ions, one that lives in the center of this cube and another that lives in the corner of the cube. They have equal and opposite magnetic moments, so it's a fully compensated antiferromagnet. But it also has a very unusual and useful property, which is that if you, okay, so the question we wanted to ask is how do you control the antiferromagnetic order here? It has this very unusual property, which is that if you strain the crystal uniaxially, you end up creating a magnetic moment, which is proportional to the applied stress, because you decompensate essentially the magnetic moments on the two sublattices. And this happens because essentially you change the in-plane cobalt-fluorine bond length. Okay? And so this is called piezomagnetism, like piezoelectricity. And it's a very useful property because it allows you to control, bidirectionally control magnetism in an antiferromagnet, which is an otherwise difficult thing to do. However, strain is slow, and you're limited to how much strain you can apply before a crystal will break. So what we wanted to explore was whether or not we could use light to emulate this effect and somehow go beyond these limitations. So at first glance, this is a bit of a non-starter because here what you're looking at is a top view of the cobalt fluoride structure. And what strain is doing is basically breaking the underlying crystal symmetry of the lattice, in which the cobalt-fluorine bond length for the center cobalt and the corner cobalt are otherwise the same. But when you strain the system, they end up with these antisymmetric distortions. One gets longer and the other gets shorter. And essentially, this leads to a change in the orbital magnetic moment, which decompensates the two sublattices and gives you the ferromagnetic order. Okay, the question is, how do you do such a thing where you want to break the underlying crystal symmetry optically? And what you have to do is find some kind of a mode in the system that allows you to have the same type of response. And it turns out that there is a B2G symmetric Raman mode in the system that does essentially the same thing. Okay, so what you see here are the distortions associated with this Raman phonon. And what you can see is that if you just look at the in-plane cobalt-fluorine bond distances, it does exactly the same thing as a strain. And so if you were to essentially excite such a mode, then the mode amplitude would give you a change in the magnetization just like strain. And the big difference here is that this is an optical phonon. So this is a volume-preserving excitation, whereas strain changes the volume. So you wouldn't be limited by the same elastic constraints as you would by straining the crystal. But the challenge is you have to somehow break the underlying symmetry of the lattice, and you have to figure out a way to excite this Raman mode, which you wouldn't be able to do optically. You can't couple directly to these Raman modes with light. So how do you do that? And so briefly, I'll explain to you this idea of nonlinear phononics. I think Van Zheng will probably talk about this more tomorrow. But let's look at what happens when you shine a laser pulse on a crystal, which is resonant, let's say, with some optical infrared active phonon, which you can couple to directly with light. In that case, what will happen is that you essentially will vibrate the lattice along the direction of that infrared active mode. But if you drive the system strongly enough, you'll also access anharmonic terms in the crystal potential, one of which is a term that couples, let's say, infrared active modes to Raman active modes. The lowest order term is one that looks like this, where the square of the infrared active mode couples linearly to the Raman mode. Essentially, what that gives you is something like this, where whenever you vibrate this mode strongly, the crystal will distort. And it will distort in one direction, such that you end up transiently, while the phonon is being driven, with a new crystal structure, which might look something like this. Okay, and this is what we take advantage of. So without kind of going into the details of how exactly the phonons that we use in cobalt fluoride, I'll just show you what happens. This is going to be a DFT simulation of the dynamics. Again, this is the top view of the cobalt fluoride. This crystal structure, if we send a terahertz pulse, which is resonant with one of the infrared active phonons, I'll show you that what you'll see is that the lattice will distort along that Raman mode. Okay, so here comes the pulse. The vibrations of the infrared active mode are starting. And over time, what you see is that you end up actually stretching this bond length here, and on average, this bond length gets smaller. Okay, that's the coupling between the driven vibration and this Raman active mode, which we care about. Okay, so essentially that's what we're trying to do in the experiment. And to make a long story short, we carried out this experiment. We drove a particular phonon that lives at 12 terahertz, and we looked at the time resolved magnetization after we drove that phonon. And what we found was that you can actually induce a magnetization via this effect. It's actually switchable. You can create a positive or negative magnetization by changing the polarization of the pump that you use, essentially changing the phase of the phonons that you drive. And I think most interestingly, what we found is that you can actually induce a magnetic moment which is more than 2 orders of magnitude larger than you would be able to do with strain before the crystal breaks. That is to say, you could strain this crystal as much as you want uniaxially until it would break. And you would achieve some magnetic moment, but when you drive the system using this sort of dynamical piezomagnetic effect, you can actually surpass that limit by quite a large amount. So this example I just show basically to give you the basic mechanisms of why driving the crystal lattice or how driving the crystal lattice can help you change magnetic behavior, but also to show you that in this non-equilibrium setting, you can get often very, very interesting and useful properties. And of course, the optical control of the lattice is something that has been around now for quite a long time, and there are lots of different examples in superconductors, ferroelectrics, et cetera. What we just showed was that you can use the same kind of mechanisms to control magnetism. What I want to talk about in the next half of the talk is actually how we can go beyond this. And one of the limitations of what I just showed you is that you have to be in the antiferromagnetically ordered phase of cobalt fluoride already in order to get this magnetization. Okay, so somehow this is still limited by temperature. What I wanted to do at the beginning, what I tried to motivate is there a way we can get beyond this sort of temperature limits of the phase diagram? So what I'll try to show you is that we can try to extend the non-equilibrium behavior of certain magnets by going to higher temperatures. To higher temperatures. So the system that we examined to look at this particular problem was a different system. It was the rare earth titanate system, and I'll explain to you in the next couple of slides why we chose this particular system. So this is a perovskite oxide system with various rare earth ions, yttrium, lanthanum, et cetera, et cetera. It has this orthorhombically distorted perovskite lattice. And what's important from the electronic standpoint is that it's a D1 system, so there's a single electron. It's spin 1/2 that lives on the titanium d orbitals. And it lives in the T2G manifold, which in the perfectly cubic case would be a threefold degenerate manifold. In the case of the real titanates, there's a slight orthorhombic distortion which lifts the degeneracy to some degree, but it's a very weak distortion, and so to a good approximation, this is still a highly degenerate orbital system. Okay, and you have essentially an electron that is shared between these 3 different T2G orbitals. Now, what this leads to is some very interesting interactions between the spin orbital and the crystal lattice. And you can understand this from a very simple, good enough Kanamori type phenomenological standpoint. Basically, if you think about the good enough Kanamori rules, if I think about 2 adjacent titanium sites, if the electron lives on the same orbital in these 2 adjacent sites, they will have an antiferromagnetic interaction. Whereas if they are living on 2 different orbitals, they'll have a ferromagnetic interaction. Okay, and so what you end up with is a situation where the magnetism is highly coupled to the orbital configuration, which is in turn dictated by the crystal structure. Okay, so you can end up with an antiferromagnetic phase or ferromagnetic phase depending on the exact nature of the crystal distortions. And this is shown very nicely in this phase diagram where basically here you have yttrium, here you have lanthanum. As you're going from left to right, the crystal lattice is getting less distorted. And what you find is that you go from a ferromagnet, you can tune the transition temperature down to 0, and you can even end up in an antiferromagnetic phase. Okay? So what we'll be looking at is this ferromagnetic case, yttrium titanate. And the interesting part about yttrium titanate is that it actually shows very peculiar signs in its thermodynamic properties because of this very strong interaction between the spins, orbitals, and lattice. Essentially, because of the proximity between these phases and the sort of strong competing interactions, you end up with very, very large fluctuations of magnetism and orbital order. One manifestation of that is that the transition temperature is quite suppressed relative to what you expect in mean field. It's only 27 Kelvin, whereas if you looked at the exchange parameters, you would expect something like 50 Kelvin. Another example is that what you find at very, very low temperatures, when you increase the magnetic field, the saturation magnetization is quite low relative to the ideal spin 1/2 value. Similarly, if you look at high temperatures above the transition, you see signatures essentially in specific heat and also in sort of phonon phonon frequencies that show you that there are short-range spin fluctuations that are very strong that live up to temperatures in excess of 3 or 4 times the equilibrium Tc. Okay, so this is a very nice system to study because A, it has very strong spin lattice coupling. So you could try to optically control magnetic order through the lattice. But B, it has this sort of precursor fluctuating magnetic phase at high temperatures that we may be able to utilize to try to stabilize a really long-range ferromagnetic order above Tc. Okay, so this was the goal of the experiment that we carried out. And the experiment is quite similar to the one that I showed you in cobalt fluoride, where we use, essentially we pump the lattice with some resonant terahertz emit-IR light pulse, and we probe the magnetization using some magneto-optic effect. In this case, we do it in reflection, so we're using MOC. And what I'll show you is a MOC signal, which is proportional to the change in the magnetization of the ferromagnetic yttrium titanate as a function of time. And the phonons that we pump are 3 different phonons, which correspond to different types of structural distortions, which in principle should change the orbital state and hence the magnetic state in different ways. Okay, and so we examined what happens to the magnetization after we drive these different phonons. And the experiment is shown here. The important point is that a positive signal here means that we've enhanced magnetization in the system, and a negative signal means we've weakened or destroyed magnetization in the system. And the first thing you can see here, these are the MOC traces for the 3 different phonons that we drove. And dotted line is the pump profile. And what you can see is that depending on the phonon that you pump, you can either enhance or weaken magnetism. And the magnitude of this change in magnetization depends on that phonon. Okay, so this is was for me a very exciting result because it shows for the first time phonon selective manipulation of ferromagnetism in the sense that it's not just the energy you're dumping into the system that matters. It actually matters what distortion you drive, right? So this is actually already an important signature that we're doing something interesting to the system. And now we can see actually what is this non-equilibrium magnetic state that we drive, okay? So what we did was we looked in more detail in particular at this non-equilibrium state that we get after driving with 9 terahertz, which is the one that has the strongest effect. So again, here I'm showing you the equilibrium magnetization as a function of field at low temperatures where you find that the magnetization doesn't saturate to its ideal spin 1/2 limit, which may be related to spin fluctuations. And what we find when we drive the system is that for the strongest drives that we can produce, we end up actually with a non-equilibrium magnetization at long times, which saturates very close now to this ideal spin 1/2 limit, suggesting that we may be kind of quenching the fluctuations that are otherwise suppressing the magnetization. I think what's even more suggestive is the fact that this is really a hard limit. When you look at the fluence dependence, it really saturates right at this value, which corresponds to essentially the ideal spin 1/2 limit. Okay, now we can see what happens when we increase the temperature. That was all at low temperatures. Now what happens when we drive the system at higher and higher temperatures is something quite unexpected, which is that you end up seeing that there's a enhanced magnetization not only below Tc, but also a magnetization that exists above Tc where the equilibrium magnetization is 0. And you can take a look at what does the magnetic state look like in this high temperature state, and it looks really like the ferromagnetic state of yttrium titanate just below Tc. So it's sort of just on the edge of this ferromagnetic ordering temperature. And we see that even up to the highest temperatures that we measure, that we end up with a pump-induced magnetization, which is at least up to more than 3 times Tc. Okay, and interestingly, if you look at what this temperature dependence looks like, it follows quite closely the temperature dependence of the short-range spin correlations that we saw in equilibrium. So again, there's some relationship between the fluctuations of the system and the ability to create this non-equilibrium magnetic order. And we can actually look at what happens now as a function of temperature when we pump the different phonons. And what we see is that, again, depending on the phonon that we pump, we can either essentially increase the effective TC or decrease the effective TC, and which correlates well with what we find in terms of the enhancement or diminishing of magnetization that we found at low temperatures. Okay, so this is, again, a phonon selective way of controlling the magnetization of the system. Now, in the last couple of minutes, I'll just try to give you an idea of what we think is happening, why this is happening. We don't have a full picture of this. We've tried very hard. I tried to work with Andy, for example, to really get a full microscopic description, which wasn't really possible. We have some kind of phenomenological idea. I can already tell you on first glance, there's a couple of things that you might think. Can direct spin-phonon coupling explain it, where you couple essentially just the exchange between the different layers by moving the lattice? Turns out that this doesn't work. Is it heating? The answer is no. Is it other optical effects? Could it be strain? The answer is no. We've looked at this in detail. Instead, what we think is happening is basically related to this very strong correlation between the lattice, the orbitals, and the spins. And you can understand this in a simplified model which couples these 3 degrees of freedom. I won't go into the details here. Basically, what ends up happening is that when you excite the lattice, this ends up modulating the orbitals and leads to a change in magnetic order as a result of that. And we can visualize this by looking at how the magnetic state of the yttrium titanate changes as you change the orbital ground state. Okay, and we can parameterize the orbital ground state by these 2 so-called orbital angles. It tells you how much of the YZ, XZ, or XY orbital you're in. And if you then make some kind of hypothetical phase diagram that's, I had the same structure, but I just changed the orbitals that the electron was living in, what would the magnetic state be? What you can see is you end up with something very complicated, where you have different antiferromagnetic orderings, you have different ferromagnetic orderings, depending on exactly what orbitals you're living in. And the interesting part is that the equilibrium system sits really close to this phase boundary between ferromagnetic and antiferromagnetic. And so if you zoom in here, you can see that this is kind of the origin of these strong fluctuations. And what we find is that when we drive the lattice, we're essentially pushing the system closer to or farther from this phase boundary, which either weakens or enhances the effect of these fluctuations. Okay, and this is also sort of verified by doing direct DFT calculations, where we find that by changing the displacement of the particular mode that we drive, we actually change the orbital energies in a way that agrees with experiment. So I was going to tell you about dynamics. I was going to tell you about heterostructures, but I think I'll stop there. And let's see, and just give you the takeaway message, which is that essentially driving the crystal lattice optically, I think, provides a really powerful way to engineer magnetic phases and also drive different types of non-equilibrium behavior that you wouldn't expect or wouldn't be able to find in usual settings. And I think of this now in my own lab as part of the suite of tools that we have to engineer quantum materials, which is one of the motivations that I had for wanting to organize such a workshop, where now this lives in conversation with all the other ways we have to engineer materials, including with strain, interfaces, heterostructures, et cetera. Okay, so with that, I will stop, and thank you for your attention.